welcome back. We're now going to get started with machine learning. So the format of these lectures will be a little bit different, but they should be pretty similar to what we did. So there's three types of machine learning. Obviously there's supervised learning, unsupervised learning, and reinforcement learning. In this section we're going to learn about the fundamental differences between the three different learning types, and using conceptual examples we will develop an intuition for the practical problem domains where these can be applied. So obviously looking at this chart you can see that supervised learning relies on label data, direct feedback, and we use that to predict the outcomes in the future. Unsupervised learning has no labels and also has no feedback, and we must find a hidden structure within the data. Reinforcement learning is a decision process that has a reward system that reinforces the learning, I guess, and you learn through a series of actions. So let's talk a little bit more just about supervised learning. The main goal in supervised learning is to learn a model from labeled training data that allows us to make predictions about unseen or future data. Here the term supervised refers to a set of samples where the desired output signals or labels are already known. So we add our labels to our training data, we develop them in our machine learning algorithm, and then when we get new data, hopefully we have a predictive model that will help us make an accurate prediction. So considering the example of email spam filtering, we can train a model using a supervised machine learning algorithm on a bunch of labeled emails that are correctly marked as spam or not spam, to predict whether a new email belongs in either of two categories. A supervised learning task with discrete class labels, such as in this example, is also called a classification task. Another subcategory of supervised learning is regression, where the outcome signal is a continuous value. So now we can talk a little bit about classification for predicting class labels. So classification is a subcategory of supervised learning where the goal is to predict the categorical class labels of new instances based on past observations. Those class labels are discrete, unordered values that can be understood as group memberships of the instances. The previously mentioned example of email spam detection represents a typical example of binary classification task, where the machine learning algorithm learns a new set of rules in order to distinguish between two possible classes, spam and non-spam. However, the set of class labels does not have to be of a binary nature. The predictive model learned by a supervised learning algorithm can assign any class label that was presented in the training data set to a new unlabeled instance. A typical example of a multi-class classification task is handwritten character recognition. Here we could collect a training data set that consists of multiple handwritten examples of each letter in the alphabet. Now if a user provides a new handwritten character via an input device, our predictive model will be able to predict the correct letter in the alphabet with certain accuracy. However, our machine learning system would be unable to correctly recognize any digits 0 to 9, for example, if they were not part of our training data set. So we did this kind of before earlier, where we tried training for the letter 6 or number 6. So this figure here illustrates the concept of a binary classification task given 30 training samples. 15 samples are labeled as negative and 15 are labeled as positive. In this scenario, our data set is obviously two-dimensional, which means each sample has two values associated with it. We've got an x1 or x2, so the y-axis is x2. Now we can use a supervised learning machine learning algorithm to learn a rule. The decision boundary, represented by a dashed line, can separate those two classes into new data, into new categories. So now we can talk a little bit about regression for predicting continuous outcomes. So we've learned in previous sections that the task of classification is to assign categorical, unordered labels to instances. We tried this with with plants. We also tried this with headlines, etc. A second type of supervised learning is the prediction of continuous outcomes, which is also called regression analysis. In regression analysis, we are given a number of predictor variables and a continuous response variable, which is our outcome or target, and we try to find a relationship between those variables that allow us to predict an outcome. For example, let's assume that we are interested in predicting the math SAT score of our students. If there's a relationship between time spent studying for the test and the final scores, we could use it as a training data set to learn a model that uses the study time to predict the test scores of future students who are planning to take a test. So this figure illustrates a concept of linear regression. Given a predictor, variable x, and a response variable y, we fit a straight line to this data that minimizes the distance, most commonly the average squared distance between the sample points and the fitted line. Now we can use the intercept and slope learned from this data to predict the outcome variable of new data. So obviously there's a very close correlation between studying and doing well on the exam, technically. And so we can see the more time spent studying, the higher the score is going to go. There's some variation, but overall it should follow this example. So now we can talk a little bit about solving interactive problems with reinforcement learning. Another type of machine learning is reinforcement learning. In reinforcement learning, the goal is to develop a system that improves its performance based on interactions with the environment. Since information about the current state of the environment typically also includes a so-called reward signal, we can think of reinforcement learning as a field related to supervised learning. However, in reinforcement learning, this feedback is not the correct ground truth label or value, but a measure of how well the action was measured by a reward function. Through its interaction with the environment, an agent can then use reinforcement learning to learn a series of actions that maximizes this reward via an exploratory trial and error approach or deliberative planning. A popular example of reinforcement learning is a chess engine. Here the agent decides upon a series of moves depending on the state of the board, or otherwise the environment here, and the reward can be defined as a win or a lose at the end of the game. There are many different subtypes of reinforcement learning. However, a general scheme is that the agent in reinforcement learning tries to maximize the reward by a series of interactions with the environment. Each state can be associated with a positive or a negative reward. And a reward can be defined as accomplishing an overall goal, such as winning or losing a game of chess. For instance, in chess, the outcome of each move can be thought of as in a different state of the environment. To explore the chess example further, let's think of visiting certain locations on the chessboard as being associated with a positive event. For instance, removing an opponent's chess piece from the board or threatening the queen. Other positions, however, are associated with a negative event, such as losing a chess piece to the opponent in the following turn. Now, not every turn results in the removal of a chess piece, and reinforcement learning is concerned with learning the series of steps by maximizing a reward based on immediate and delayed feedback. So while this section provides a basic overview of reinforcement learning, please note that applications of reinforcement learning are beyond the scope of this lecture, and we're primarily focused on this course on classification, regression analysis, and clustering. So now let's talk a little bit about discovering hidden structures with unsupervised learning. So in supervised learning, we know the right answer beforehand when we train our model, and in reinforcement learning, we define a measure of reward for particular actions by the agent. In unsupervised learning, however, we are dealing with unlabeled data or data of unknown structure. Using unsupervised learning techniques, we were able to explore structure of our data to extract meaningful information without the guidance of a known outcome variable or reward function. Clustering is an exploratory data analysis technique that allows us to organize a pile of information into meaningful subgroups, otherwise known as clusters, without having any prior knowledge of their group membership. So we talked a lot about this before. We did a few lectures on clustering. Each cluster that arises during the analysis defines a group of objects that share a certain degree of similarity but are more dissimilar to objects in other clusters, which is why clustering is also sometimes called unsupervised classification. Clustering is a great technique for structuring information and deriving meaningful relationships from data. For example, it allows marketers to discover customer groups based on their interests in order to develop distinct marketing programs. So this figure illustrates how clustering can be applied to organizing unlabeled data into 3 distinct groups based on X1 and X2. This is X2 going up, and if it's hard to see on your screens, you can see that we have 3 circles here, and the data seems to be fairly concentric or in these spots. So dimensionality reduction for data compression. Another subfield of unsupervised learning is dimensionality reduction. Often we are working with data of high dimensionality. Each observation comes with a high number of measurements. That can present a challenge for limited storage space and the computational performance of machine learning algorithms. Unsupervised dimensionality reduction is a commonly used approach in feature pre-processing to remove noise from data, which can also degrade the predictive performance of certain algorithms and compress the data into a smaller dimensional subspace while retaining most of the relevant information. Sometimes dimensionality reduction can also be useful for visualizing data. For example, a high dimensional feature set can be projected onto 1, 2, or 3-dimensional feature spaces in order to visualize it via 3D or 2D scatter plots or histograms. The following figure shows an example where nonlinear dimensionality reduction was applied to compress a 3D Swiss roll into a 2D feature subspace. So you see we just unrolled this guy, and this what was 3D is now 2D, and now we can see all its dimensions clearer. We can see that this purple area is much wider than the red area, which was difficult to see this way. So we're going to be working on some more examples from our IRIS data set, and this just is an image that shows you what we were talking about before when you're looking at 3 different species of iris. So you got setosa, versicolor, and virginica, and you've got the petal, the sepal. So let's just move on to the roadmap for building machine learning systems. In previous sections, we discussed the basic concepts of machine learning and statistics and the 3 different types of learning. In this section, we're going to be discussing other important aspects of machine learning accompanying the learning algorithm. The following diagram shows a typical workflow for using machine learning and predictive modeling, and we're going to discuss this in the following subsections. So you might want to refer back to this if you ever get lost or wonder where we're at in machine learning. So there's pre-processing, which is processing the data, and that includes statistics sometimes. The learning algorithm is in the middle. Our final model, we apply labels, and then we're introduced to new data. So this is during the evaluation period, and then we get new data, and we are trying earnestly to make accurate predictions. So that's our hope with machine learning. Briefly, let's talk a little bit about pre-processing before we let this section go. Raw data rarely comes in the form or shape that is necessary for optimal performance of a learning algorithm. Thus, pre-processing of data is one of the most crucial steps in any machine learning application. For instance, if we take the iris flower dataset from the previous section as an example, we can think of raw data as a series of flower images from which we want to extract meaningful features. Useful features could be color, the hue, intensity, height, flower length, width. Many machine learning algorithms also require the selected features are on the same scale for optimal performance. So we try to transform features into a range from 0 to 1, or a standard normal distribution with 0, mean, and unit variance. So just so we can compare across. Some of the selected features may be highly correlated and therefore redundant to a certain degree. In those cases, dimensionality reduction techniques are useful for compressing the features into lower dimensional subspace. Reducing the dimensionality of our feature space has the advantage that less storage space is required and the learning algorithms can run faster. In certain cases, dimensionality reduction can also improve the predictive performance of a model if the dataset contains a large number of relevant features. That is, the dataset has a low signal-to-noise ratio. And remember, when we test our machine learning algorithms, we must also divide our data set into separate training and test data so we can see whether or not our algorithm will generalize well to new data. Okay, this wraps up our first lecture in machine learning, and I look forward to talking to you guys in the next lecture. Thanks.